Very good morning, all of you. Today we are at the third session of this course on responsible artificial intelligence, which is a collaborative effort by Pune Knowledge Cluster and Persistent Systems. And today we have with us as a speaker Mr. Dattaraj Rao. He is the author of the books Keras to Kubernetes, the journey of a machine learning model to production. Mr. Dattaraj leads the Artificial Intelligence Research Lab at Persistent, which is responsible for driving through the leadership in AI and ML across the company. So we are very happy to have you here, sir, today for the session. And over to you.
Thank you. Can you hear me? All right.
Yeah, yes, we can hear you.
Okay. Hi, everyone. Thanks for the nice introduction. My name is Dattaraj. So I'll take the third session on the course on responsible AI, and this is session is interpretable and explainable AI, part two. So in the last session, as you saw, Dr. Bhushan covered the basics of interpretability and explainability. And I'll talk about, and I think he mainly covered about structured data. So I'll get into more of unstructured data like text and images, and how we can, what are some of the approaches to explain these unstructured data. I was supposed to have this with Dr. Mukta, but she's unwell, so she could not make this session. So I'll pretty much cover this session. So I'll try to have certain breaks, and I want to make this interactive and also more hands-on, hopefully. So earlier I distributed some of these Google Colab notebooks, which will actually let you run the exercises on your own parallelly with me. So I'll take two breaks during the session where you can, if you have not already done, just set up the collab with your Google account. It shouldn't take more than 5 minutes. And then we can, once the exercise starts, we can walk through it maybe ideally together, and you can see the results being generated, and you can even tweak the values. So hopefully we can make it more interactive and hands-on session. Uh, I hope, are you seeing my screen?
Yes, we are able to see a screen.
Okay,
Yes.
so just so this as I said, Mukta could not attend, and this again, like last time's with Bhushan session, these are I've compiled this material a lot from different sources on the internet and papers, and I've given references. So a lot of these views are of mine and Mukta's, and so today's session, I'll start with, we'll just revisit some of the basics of explainable AI, and most of this Bhushan already covered. We'll talk about image data and how the image data is different, some of the basics. And for you, this may be more of revisiting basics, but just stay with me. We'll just cover what image data looks like, getting into how a convolutional neural network works very quickly. And then we'll get into an exercise where we will try to explain an image using one of the popular approaches, GradCam. Then we'll get to text data. We'll look at we'll try to look at some of the evolution of natural language processing, how over time, over the years, natural language processing has evolved. What are the state of the art today, like transformers? And then talk a little bit more about transformer architecture, and then getting into explaining transformers. And most of the material that I've compiled, we have compiled, is kind of through these papers, which I have added as references at the end. So I highly encourage you after the session, go through the references, because that will make it a lot of the concepts much clearer. And at the end, hopefully, I'll have some time for questions. So feel free to, I mean, you may interrupt in the middle and also ask questions, or we can reserve questions at the end, either way. Let's get started. So getting into the explainability basics, as we saw last time, we could have looked at local explanations, and one of the popular approaches that is used here is the LIME, the top left, and this image is directly from the LIME paper. So LIME is basically local interpretable model agnostic explanation. So what LIME does is it tries to build a linear local model for each data point. So for whatever the prediction for each data point is, it tries to explain it using a sparse linear local model, so that you can tell which feature, like in this example, the sneeze, headache, or no fatigue, which was the feature that was used to make a decision that the person has a flu. So Lime focuses on local, it's pretty popular, but then it builds a surrogate model. Uh, the other approach that is very popular is SHAP, which is Shapely Additive Explanations. Now, SHAP is based on game theory. So the idea here is like in a game theory, when you have multiple players contributing to an outcome, you kind of allocate a certain credit for that particular outcome for each player when you work together. So SHAP kind of borrows on that approach where you have multiple features, like in this is pretty much the diagram from the SHAP GitHub. When you have multiple features like age, sex, blood pressure, BMI that contribute to a particular output, uh, how much contribution, positive, negative, each feature has. That is what SHAP tries to measure. So SHAP assigns a SHAP score to each feature, each data point in your training set. So that, and that is used to kind of explain your predictions. So now, SHAP can be used for global predictions where you can summarize, put a SHAP beehive plot or a SHAP bar chart showing which features are important overall in your training set. And at the same time, SHAP can also do a local explanation, like in this example that is shown on the bottom right, where we are actually explaining a text here. There is a text, what a great movie, and if you have noticed. So it's kind of a contradictory statement, but SHAP tries to identify the positive and negative based on the words that are available. So these two approaches are the ones we'll talk a lot about, Lime and SHAP, extending from Dr. Bhushan's talk. And then we'll focus on images and text. So text example you see there, the image example is on the left bottom. And I'm sure this was also covered in last week's session. So basically, this is a famous example in Explainable AI, where there was a classifier built to detect wolf or a husky classification. And the training data that was fed to that particular classifier, all the images of wolves had snow in them. So the classifier ended up uh, finding any animal with a snow background and classifying it as a wolf. So it was not looking at the features of the animal, but it was looking at the features of the environment, which was a big. So when they did this analysis, they could find that what the model was seeing, and these are the pixels that were of importance. So for an image, what we try to do is figure out which pixels are more important to make the prediction. And in this example, you see on the bottom left, the snow pixels were the ones that were used for making the decision, which was incorrect. So what explainability methods that we see, and these become more prominent in images and text because it's not a direct explanation. So if you look at like your structured data, you can clearly see, do like a random forest and do a feature importance plot. But now in pixels, it becomes a little complicated. You have to see which pixels contributed to that classification and how do you calculate that, which pixel is more important. Same way for text, how do you calculate which word is more important or which words were more important, collection of which words that classified that text as a positive or negative sentiment. So that those are the examples that we'll cover, and some methods I'll show, which will try to explain this. So that's kind of revisiting some of the explanative basics. We'll jump into the image examples. So a little basics, and just bear with me here. So just some basics of image processing. I'm sure you guys have seen this. Read about this a lot. So typically, an image, a way a computer represents an image, will be a collection of pixels, and the width and the height of the image would be the array's dimensions, and the number in the array will be the intensity of the pixels. So the intensity could be in a grayscale image, a number between 0 to 255 usually. But if it is a color image, right, in the right hand side, you could have three channels, so three color channels indicating red, green, and blue, and that three-dimensional array becomes your what the computer sees. Now you need to build algorithms that can analyze that three-dimensional array and map it to a classification. So if you want to see that this image is of a person, you have to somehow convert that three-dimensional or two-dimensional array in case of grayscale. Sorry, two-dimensional array in case of grayscale to map it to a classification among certain classes. And that is what the most popular technology for this is convolution neural networks. So just some basics of convolution neural networks. The image of the bottom left, that shows the example of a convolution process. Now, as I said, what you are doing is taking a three-dimensional image and mapping it to say 1,000 classes. So you want an array which will which will pass through a softmax layer and give you a distribution over 1,000 classes with the highest number between 0 and 1, telling you that is most likely the class with that confidence. So for that, some of the methods, techniques used is, one is convolution, where you actually pass a fixed filter. In this case, it's a 3 by 3 filter that passes over the entire image. And it pretty much just does a mathematical convolution, just does an averaging, multiplies that convolution filter by the individual pixel values, and assigns that to the new pixel in the next layer. So multiple convolution filters are passed. So you get convolution layer is one of the most prominent in the CNN. And then to reduce the size of the images, you use a pooling layer. So pooling layer, all that it does is, as shown on the bottom right, it takes the images, either does an averaging or finds the maximum intensity of the pixel, and gives you a much smaller uh, array. So what happens in the process of convolution, if I move to the next slide, is basically you start with your three-dimensional pixel array. You keep adding this convolution filters, a mix of pooling layers, and you divide that into a much wider but a smaller array. So you start with a width by height into 3 image, and you reduce into a box like this, where the number of features increases. Like you start with just 3 channels, like 3 color channels, but now you increase the features and you reduce the size of the image. And then finally you flatten that image and map it to using a softmax layer to certain categories. So finally at the end, you want to have a like 1,000 categories array with the argmax of that array telling you which category this image belongs to. It's a car or a person or something like that. So that's typically how a convolution neural network would work. And there are different architectures, VGG, Inception, ResNet. I mean, computer vision with new papers, a lot of new architectures are being proposed. So one of the popular ones and relatively older ones is VGG 16-layer architecture. And this is how it looks like. This is an image from keras.io. And this is directly available in Keras. We'll actually use a pre-trained model to load VGG 16 and show it in an and help it to analyze an image. So basically what it does, if you look at the bottom image, you takes the image of a car and reduces it from a, so VGG 16 expects the image to be 224 by 224 by 3. And it keeps applying your feature maps and max, your convolution and max pooling layers to reduce it into a 1 by 1 by 4096 array. And then applies a fully connected layer to make it a 1 by 1 by 1000 array. So the 1000 array is because for image classification, the most popular reference is ImageNet. ImageNet is basically a library of images which are pre-classified. So these are labeled images, so you can treat them as your ground truth with 1000 categories. So if VGG16 can predict one of those categories from ImageNet, I mean, then you can clearly say that this image belongs to this class. That's what VGG16 or this convolutional neural networks tries to do. So just a bit overview of ImageNet. Moving to the next slide. This is what, so there are pre-classified images. So you have VGG16 architecture, you train it on a huge data set like ImageNet. And this was something that the computer vision community actually established as a benchmark, that, okay, now you have this ImageNet data set, you train your model in ImageNet, figure out your accuracy on the ImageNet data set. So you can say that any image can be classified accurately to a particular category out of the 1000 categories. And then that becomes your kind of a benchmark. And the newer architectures like Inception, etc., they try to compare against ImageNet to see how well they stack up against the state of the art. So that's kind of a very high level overview of CNNs and how ImageNet works. Now we'll get to the second aspect of how do you explain images. So over time, there were different architectures that were proposed to explain your images. And basically what you mean by explaining images, like you saw in the last week's examples, if you have like a banking use case, loan fraud or something, you can say that because the income is high or there are existing loans, you can kind of reason that because of these features, you predict this classification. Now with images, it all depends on pixels. And an individual pixel doesn't really tell you, like if I tell you that pixel number 200 by 20 is green, it doesn't tell you anything. So what really helps is a combination of pixels. So images are spatial in nature. So you want to know that this set of pixels is what is where the image sees. So what you can say is the image looks at this sets of pixels, and based on that makes a decision that this is a wolf or a husky, or if this is a person. So that is what you want to figure out. So the algorithm that you want to build is you want to figure out which pixels are used to make the classification. So some of the earlier approaches were more around like there was an algorithm called look only once. The idea was you take an image, and now a classifier is saying this is a particular class. You hide certain pixels. So you take some strategy, like maybe just run a sliding window and hide these pixels. And once certain pixels are hidden, you see if you get the same classification. So that's the look only once. And whichever pixels when you hide, you cannot classify correctly, those are the important pixels, and you try to flag those pixels. So that was one approach. But then over time, and advantage of that approach was it didn't really matter how you were training your network. Is GG60 or any, all you needed was a prediction from your model. So that was a pretty good approach. But then that was not that it was not that accurate. So better approaches evolved, which kind of look at the gradients of image. So we train this images, we train a CNN using the gradients, using back propagation, as you know. So you use these gradients to see if they can classify, they can help you detect which pixels are more important. And that algorithm, one of the most popular ones is GradCam. And I'll just talk about GradCam. This is a schematic that is from the GradCam paper, but we kind of modified this a little bit. And just to simplify it for this explanation. Uh, so basically what GradCam does, it starts with an input image here, this image of a dog and a cat. It passes through a regular convolution network, which could be your VGG16 or any network. And as we saw earlier, what the CNN does, it creates a feature map. So it takes your three-dimensional width, height, and channel dimensional image and puts it into a feature map, and takes the last activation layer, flattens the layer, and gives you a 1000 layer array, which will tell you if it is a cat or a dog. Now, what GradCam does is it takes your the class which is selected, it propagates that data back into the feature map and takes the last convolution layer. So if you see, if you go back to the convolution neural network, what it does is as it maps your three-dimensional image to your classifier array, the classification array, the uh, the individual feature maps that are identified, these kind of try to look at certain aspects of the image. So for a cat, there are certain feature maps that are found, like you can see maybe the whiskers of the cat or the face of the cat, that will be identified. Those are captured into your feature maps. So when you take the last convolution layer and take a weightage, you take the gradients and take a weightage, because the last convolution layer will have multiple feature maps, because you have multiple features, convolution features running. You take a weighted average based on the gradients, you apply a ReLU activation to it, and then you get a heat map. And we will actually do this exercise shortly. So you get a heat map, and the heat map will tell you which pixels were more important based on that gradient weighing that you just did. Which pixels are more important, which pixels are less important. So heat map will tell you that in this example, if you see these pixels which are shown in red are more important, and the algorithm, the neural network, use those pixels to make a decision that it was a tiger cat. So then what you can do is you can take that and superimpose it over the original image, and you can clearly say for the cat category, the category of a tiger cat, these were the pixels that were more important, and because of this, that decision was made. So this is how GradCam works. You take take one of the last convolution network layers for that particular class which was activated. You do a gradient weighing on that, so that you know which pixels are more important, and you create the heat map. Apply the heat map onto your original image, and you can find out which pixels were more important. So that's kind of an overview of how GradCam works. Of course, with GradCam also there will be some limitation. There are more accurate methods. There is integrated gradients, which like GradCam tries to generate a heat map. Integrated gradient tries to start from scratch and tries to see which pixels lead to that activation. But those are much more, and I have some references on those. Those are much more advanced methods. I highly encourage, if you're interested in this subject and computer vision, you can look at some of these papers around integrated gradients or blurred integrated gradients, and you can understand more of this algorithm. But the beauty of this is this really goes into details of how the convolution neural network works, how the gradients are used and how you do the weighted gradients and try to get your GradCam heat map. So that's kind of an overview of how GradCam works. And before, and then the other approach to doing convolution, to explaining convolution neural network, you could also use Shapley explanations. You saw examples of using Shap to explain features. You can apply the same thing to images. Like in this example, what you could basically, what Shapley does is assigns weightage to pixels. So instead of using this gradient method, what you do is you see which pixels were more important to, I mean, that also uses gradients, but you try to see which pixels are more important for you to come to a decision. Like in this case of it, I mean, it identifies instead of a school bus, it calls it a minibus, but then it says these pixels in red are the ones that it used to make a decision. So the approach is the same. You create a heat map from one of the layers to figure out what the convolution neural network says, and then you overlay that heat map on your image to explain that image. So that's kind of the general approach. Just there are clever techniques like Shapley values or your GradCam to explain your to build that heat map. I mean, that's how you explain images. So that's kind of the first part of my talk and how we are explaining your images. So now let's jump to the exercise. So the second half, of course, will be the text, explaining text. So before we go to the text, let me go to the Google Colab, and I'll take a 5-minute break now. We'll start at 10:30. But if you are not already in, gone to this, basically Google Colab, just give you a quick 1-minute update overview. It's basically a notebook, a Python notebook in the cloud. So you can connect to it. You can either create a GPU runtime and basically GPU or a CPU runtime and run your Python examples through the notebook step by step, so that you can know, I mean, you can go through the entire code and see the code running right there. So we'll take this example of this notebook. So and this was already given uh, in the prerequisite. So I'll give like 5 minutes. We'll start at 10:30. If you're not done it, maybe you want to open up the notebook, and if there is any installation issues, you can sort them out, and then 10:30 we'll come back and go through the notebook. Okay, I think we can get started. So there was one question on the, yeah, there was one question by Dr. Sham Sundaram on if the GradCam uses the same size of the grid as CNN, and typically, yeah, the GradCam size of the grid, and I think if I understand you right, it will depend on the on the convolution layer that you select. So for that, because as you come down the CNN, your convolution layer size decreases, and so that is the size of the heat map or grid you'll use, and then you have to upscale it to match the image. And I think we'll see that in the exercise also. So I just connected to my Collab notebook. A lot of the material on the slides is actually available in the notebook also. So I like Google Colab because you can add in content there. So the example of this, the VGG16 architecture that I showed, and then ImageNet, and then this is a very, it's a refined diagram of GradCam. This is from this link by B8SO2. This is from a blog. I think that's a nice diagram which I liked. I also included that. So this is how your GradCam would work. And what we'll do is let's we'll use the Keras and TensorFlow. So so basically, this code is putting some helper functions to create take your image and convert into a NumPy array. So NumPy, as you know, is the Python library for numerical processing. And then I have a function for displaying the images. These are just helper functions that I write. What I'll do is I'll take one, I'll preload a VGG16 model from Keras. Okay, this is not valid. It's 224. I'll take the last convolution layer name, and then I'll uh, I'll take one image of a traffic signal. Sorry about this. I removed this part. So what it is doing is it is downloading this image. So I'm going to process this image, and I've downloaded that the VGG16 model in Keras. Uh, Now the main function that I use is called make gradcam heat map. This actually function I have directly taken it from the examples on keras.io. So Francois Cholet, who is the author of Keras, he has given a very nice example of using gradcam in Keras. So pretty much this, and in the references I have that link also, so you can refer to that. I just simplified it so that we can put it in a notebook and simplified it so that we could use it. The idea here is yeah, now in a regular pre-trained CNN, this VGG16 is trained on your ImageNet data. It can directly take any image that you give, 224 by 224 image, and predict for you the classification of 1,000 categories of ImageNet. Now, what we do here is we use Keras to build another model that will take the inputs, but it will also give you one of the intermediate convolution layers. So it will not just give you the output classification, which comes after softmax, but it will give you the layer before softmax, which is your convolutional layer, because we want those activations, that activation map, and then take a weighted average of that. And then what the next part of code does is it for that particular prediction which was done. So typically this is for the argmax of your class which was selected, but you could do it for any other class also. So assuming this is for your argmax of your class, what it does is it takes the weightage average of your gradients using this gradient tape function in TensorFlow, and gives you a heat map. The heat map size is equivalent to your to the convolution layer size. And then so this is the heat map that is created. It is created by taking the last heat map layer and taking the pooled gradients. And this is the heat map that is returning as a numpy array. That's what this function does. So this is the most important function. I mean, it is very well explained, and actually it has got very good comments. But these are from the Keras Francois himself. So I suggest you just read through the comments, and this will kind of be clear. So now I'm taking the loading the VGG16 model, and Keras summary function tells you what the layers of the model are. So now it will take some time to download this model. Uh, so we have this input layer, which is 224 by 224. And each layer in your convolution neural network, like we saw, is given an ID or a name. So there are two convolution layers, a max pooling layer, then two convolution, then max pooling. And this keeps going. And this is something that they have done through trial and error. This is what is unique of the VGG16 architecture, the way the convolution and pooling layers are structured. And then finally, once you have the block 5 pool, that is where you get the feature map of 7 by 7. So this 7 by 7 is would be your final grid that you have. And then 512 is the number of final features that you have. So what for feature maps? So 512 feature maps would be different elements of the image that it would look for. Like in case of a car, it would maybe it is looking for tires, it is looking for windshield and things like that. And then you flatten that out and have two dense layers, which finally gives you a 1,000 node predictions layer, which is your softmax layer. So what we'll do is now we need to take an image that we earlier downloaded and change it to a 224 by 224 image, and pass this to the pass this to our VGG16. So first we'll make a prediction. So take the VGG16 model as it is downloaded from the Keras repository, and then we'll convert it into a 224 by 224 image and make a direct prediction. So we just do, in this case, it is just doing inference. We are not doing any retraining. So we'll just take your image and go through the steps of the convolution. And once it has classified this image, it is giving me the top categories. It is finding traffic light. It is finding this calling this as a tow truck and a fire engine. So VG16 is not always the most accurate model. As you get into more of inception and ResNet, things get more accurate. But we can at least for explanation, it's more simplistic because all it has is convolutional and max pool layer. So we should be able to do with this. So what we'll do is we'll look at three layers. So we'll look at the layer IDs first. So we look at block 1, block 4, and block 5 pooling layers. So this is where the layers are. So this will also tell you how a convolution layer starts looking at images as it starts classification. So we look at 3 layers here, and for each layer, I'm creating the heat map using that function that we defined earlier, and then I'm displaying the heat map. So now the thing is, each layer will have a different size, as you see in that. So block 1 convolution versus block 5 pooling. If you look, block 1 convolution will have a, so block 1 will be the first convolution layer. We'll have a 224 by 224 and 64 feature maps, while block 5 will have a 14 by 14. So what we'll do is we'll uh, take the heat map, and then our display image function will just normalize and give it a standard size. So we'll just convert that. So what we see is the uh, first block 1 convolution that we see. It is seeing the entire image. These are the, so it is seeing all the different aspects of the image. Multiple pixels are being seen. So it is converting from your 3 pixels, 3 color channel uh, image to this this initial feature map, which is like a 64 channel feature map. So this is the 64 channel image that it is seeing. But as you go down, as you become block 4, certain pixels get more prominence. And finally, when you uh, get to the actual image or get to the final layer, block 5 layer, you get to see that this is the pixels which are visible. And again, one thing I missed is, what I'm trying to do is look for prediction index 920. So prediction index 920 is for the first for the first uh, classification. So when you say prediction index 920, out of the 1,000 categories that ImageNet has, there is a published list which tells you what is 1,000 categories are. So I want to know, when I classify the image as a traffic light, what are the pixels that this particular image uh, 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 are being shown as more important for that particular classification. That is exactly what I'm doing. So in the earlier convolution layers, you get to see all the pixels, but as you go down, you get to see these are the pixels of important. And so the earlier question, your heat map now is 1, 2, 3, 4, 5, 6, 7. 7 by 7 is your grid size for the final, and that you extrapolate and put it on the, make the size of the image, and that will tell you exactly which portion of the image. So if you can clearly see, and I could have superimposed, I didn't do it for this demo, but in the Keras example, they've actually also superimposed. You can clearly see that this is where your traffic light is. So this model seems right. So when you start building classification models, when you take the approach like GradCam or integrated gradients, you can clearly do a superimposition. And in fact, now we have this ML pipelines, which is becoming big, especially in the when you deploy models to production. So you want to have your pipeline, if you have an image processing pipeline, have an explainable AI component to it also, which along with your classification tells you like a heat map of why that classification was made, because that will give you much more confidence to a human decision maker that this image is actually you're doing the right classification. So that's how that's how GradCam works. We walked through it. We had the GradCam function. We took a looked at the convolution layer inside, and I suggest you look at the entire network and see what some of, you can change the layers here in the array that I had. And like the Keras example, they just take one layer, but I took 3 of them. But you can try different layers, and you see for the different activations, and you can try with different images also. You see if this VGGNet or even some of the other models like Inception, if they are looking at the right pixels, if the classification is correct, if you can give some more confidence to that classification. And then the same thing you can do with Shapely explanations. So the second part, as we saw earlier, Shape basically assigns some Shapely numbers, Shapely values to each feature. And because of that, it tells you if it is a positive or a negative impact for that particular classification, for that particular output. So same thing we do in Collab. You'll have to install Shapely. So when you do Google Colab, it doesn't TensorFlow, Keras, and all it by default supports. But for Shape, you'll have to install Shape. It's pretty straightforward. You just do a semicolon pip install, and I'll download the same images was of the traffic signal. And now what I'm doing here is I again create the same VGG16 model. I get the image. Now here, this is this JSON. If you open, this will give you all the classification, 1,000 classifications of the ImageNet. So I'm reading those 1,000 classifications and giving the class names, and then I'm creating a explainer, a shape explainer. That explainer will tell me, it will basically like shape does. It will assign shape values to each of your pixel in that image. So now once that is done, let us decode that explainer. So now we can see that for the two images that I have, traffic and school, uh, school bus, for for the classification that it did, and this will take some time. So for the classification, for the class that was highest activated in that class, in that experiment, we can see the pixels, how the distribution of shape values is, and whichever pixels are the most concentrated, those will be highlighted, just like we saw earlier. So it's this is also taking advantage of gradients, but is assigning a shape value based on the gradients. So you can see here, it is looking at these. Now this is a different classification because it is finding the cab as a bigger activation in this example using shape. But then in this case, it is this is the example we saw earlier. We are classifying this as a minibus. Again, you can see the concentrated pixels are the ones that it's using for making decisions. So again, this is an approach using shape. So you can also try out multiple images and even multiple models. Like instead of VGG16, you can take a more accurate model and see if shape gives you a better way of explaining your images. So that's kind of yeah. So that's the notebook of explaining images. You can walk through this and and try it with your own images and also try it with your own models. So let me see if there is any. So I was just looking at the questions. Yeah. So Abhijit had asked. So the third picture is a superimposition of the 5x512 7x7 grid for the light class. So let me just check. Yes, the third, yeah, that is correct, Abhijit. The third picture here is the superimposition of the, it's 7x7 matrix, but 512 is your feature map. So that feature map, you take a weighted average using the gradients method. So convert it into a just 7x7 image. So instead of the 512 array, you just flatten it into a single two-dimensional array, and that is the superimposition on top of your 224 image. So that's the. I hope that answers the question. So this was the first example exercise that we did on image. So now let's move back to the slides. Uh, and keep the questions coming, and we'll take a break at the end also for more questions. So now let's go to the next part of the talk. We'll look at text classification. So we saw images, and images we are focusing on pixels for the criteria or the features, I would say, to classify your images. Now for text, it's a different story. Here we have this text is like image you can see as a single array. Now, text is a sequence, basically. You have a sequence of sentences and divided into words. So what are some of the key outcomes that you're looking at for text classification? So when you look at natural language processing, uh, so when you look at natural language processing, you can typically look at some traditional outcomes like a part of speech tagging. So if you have a sentence, you want to see, is it a verb, a particular word is a verb or a noun. So you can tag parts of speech. You can categorize text. So you can you must have read about this sentiment classification of tweets. You take a tweet or a text and say, is it a positive tweet or negative tweet? You look at named entity recognition. This is very popular in the industry, where you take a document and you try to identify entities like diseases, symptoms. In the healthcare space or in banking, you look at like some of the loan interest rates or tenure or things like that. So you want to identify these entities in your text, which words or combination of words together form your entities. Then you have this syntactic parsing, your machine translation, translate from one. Now most of the translation today is happening online. You can just translate from English to French or just by typing it on Google. So underlying below it is a natural language processing model that will do your machine translation. Then we get to the advanced aspect, which is natural language understanding. Now here we get into things like relation extraction, dialogue agent, semantic parsing. So you look at so identifying entities is pretty much like you can do by matching through vocabulary or some sentence structure. But when you look at relationships, like a disease or like symptom is linked to a disease, now that you need to extract relationship. That gets to the higher level, how to, and some of the advanced language models like BERT can do that pretty well. They can extract relationships. You can do sentiment classification. You can do text summarization. So some of these outcomes are around summarize, and we may actually look at an example also where we take a text like a big article, Wikipedia article on quantum computing, and then you can do a summarization of that. A summarization can be extractive, where you can only highlight certain sentences, saying that okay, these sentences are important. You make a summary, but that doesn't really capture the true essence. What really the advanced language models like this transformer architectures, BERTs is trying to do is get into the abstractive space, especially models like GPT-2 and GPT-3. You're actually getting into an abstractive space where you read the sentence. It's like a human would do. I would read, if you read a document, you can paraphrase it in your own words. And that's exactly what modern language models like GPT-3 can do. So advanced summarization and question answering is getting into more of the abstractive space rather than the extractive space. So just a quick, on the top half of the slide was some of the things that NLP covers. So it's a very vast area. Like image, you just have like either image classification, object detection, segmentation. But here there are a bunch of things you can do with text. So there are different types of models that are evolved. So over time, if you see in the 90s and the 2000s and 2010s, a lot of models where the text models were more based on linguistic rules. So based on the sentence structure using regex and things like that, you could say, okay, this is this is a noun, this is a verb. So they were more based on fixed hard rules, or there were statistical models where you would just take a bag of words, like because this particular text had more of happy or good or positive words, you classify them as positive. So you don't look at the sentence structure, just look at it as a bag of words and use statistics to classify. So those were the earlier NLP space. Then a real advent of NLP was around in 2014 space, where the word to vec and word vectors were introduced. So word to vec was more of representing words as vectors, just like you're representing your image as a three-dimensional array. You're representing your word as a vector of, say, and typically these words will be a single dimension. So it will be like 512 dimension word. And then, but they captured the meaning of your text corpus. So a word, and I'll show this in the next slide. A word to vec model would put words similar to each other together. And then the next evolution was more recent, especially 2018, 2019 were more like really advanced years for NLP, where the transformer architecture was evolved. BERT and models like GPT-2 and GPT-3 really transformed and achieved state-of-the-art results on different text benchmarks. So the idea was this was using the transformer architecture. So earlier it was more of word to vec, and then word to vec would feed into a recurrent neural network like an LSTM. But then these could not be parallelized because again, text was a sequence. You had to handle the text as a sequence. But as you got into BERT and transformers, these models could be parallelized because they use something called self-attention. So you, by looking at the same sentence from either direction, you could try to see which words were more important for that particular sentence. So using self-attention mechanisms, BERT and transformer models achieved really state-of-the-art results. And now, as we get into 2021, we have these modern models like GPT-2, which are auto-regressive. They support this abstractive, what I was talking about earlier, abstractive text generation. So they can look at your text and they can generate the next word in your sentence. Also, a very popular technique has evolved, which is language pre-training. So one of the things about text is you have so much text which is unlabeled. Your documents and documents of text, which is just pure text. There is no labeling on it. Now, if you can learn from unlabeled text in an unsupervised manner without labels, that is language model pre-training. So you understand your patterns in your language, and then use those patterns to train a downstream task, like your either name entity recognition or question answering. So that's the new evolution of NLP, of using models that are trained in a that are pre-trained using unsupervised manner, and then downstream they are fine-tuned for a particular task like name entity recognition. And now, I mean, I've shown 2020, but getting into 2021, some of the newer models, so if you look at GPT-3 or T5, especially T5 is the text-to-text transformer, is one of the latest models. It basically takes a text input and gives you a text output. So if you want to summarize a document, all you have to say is summarize and give the document, and it will give the text, and it will create a summary for you. So new models like GPT-3 kind of, they are getting into this AGI kind of space where you just tell it what to do, and it will do it and give it back to you. You just have to tell it in human language. So that's kind of the evolution of NLP. So some of the key milestones, as you see, Word2Vec is one of the major milestones which moved from the statistical space to your actual machine learning space and more recurrent neural network space. Transformer architecture, which really changed the game for the language models and established the new benchmarks in the state of the art. So we'll talk about some of these models and how we can explain some of the like earlier statistical models like latent LDA, and these can be explained like similar to images that we saw. But then we'll try to focus more for this class on some of the advanced models like transformers and how we can explain those. So just just a quick thing on Word2Vec, and this may be something you already covered, but the idea was that you define this words as from the corpus into a vector space, so that when you can do some word arithmetic on it. So the popular example is you can map a king and a queen, and a similar distance in Euclidean space. If you do a PCA and reduce it to just 3 variables, similar pattern shows between man and a woman. So if you and you can actually do some arithmetic, you can say king plus man minus woman, and you'll get queen. So things like that can be done using word vectors, because these are just vectors which are 512 dimension vectors which represent the words, and similar words context are together in the Euclidean space. So you can see that like capitals in this country and capital, you can say that when Spain and Madrid, the distance, Euclidean distance and the direction will be the same. And similarly between Italy and Rome. So you can just do Italy versus Rome subtraction of those word vectors. You can get the same Euclidean distance as you will get between Spain and Madrid. So what you are converting here, just like you did with images, taking an image and converting into an array, you are taking a word and converting into vectors, and now feeding that vector into a neural network. And the neural network that is used, because this is a sequence model, you need to use a recurrent neural network. So the idea of recurrent neural network is it takes a sequence of inputs of similar dimensions and passes it between over the space. And also one of the inputs is fed back to itself. So it's like a recurrent, it's a recurrent connection. You pass the inputs forward as well as you have a reverse connection and to the same layer. So that's how recurrent neural network works. Again, drawback of this is because the sequence has to be handled together, you can't really parallelize. You can't take advantage of GPUs or the advanced parallelized hardware. So that has been a limitation. Performance has been a low. So that's what has been countered using some of the things like transformers. And we'll talk about transformers in a bit. So let's take an example of Lime. So when Lime does a text explainer, again, Lime is more local explanation. So what it does is it takes a single prediction. Like in this case, this was you took a corpus of text in an email. So this was trained on your the News 20 data set, which has multiple emails, and you have to classify those emails. Those emails are classified into certain categories like graphics, medicine, politics. In this case, this particular email, if you will see, it was classified into as medicine. So, and the reason it was classified into as medicine, you can build a local model and say, because these words were involved, like disease, medicine, and medical, you can see here. And then this is cut, but you will not see the other part, but you can say in medical school or treatment of a disease. So as it looks at certain things, so these words are of interest, it looks at those words, and because of that, Lime classifies this as a medicine. So this is an example of a Lime explanation for your for your text. Similarly, we can do with Shep, and Shep, again, the same concept, Shapley additive explanations. It assigns for each word, for each word in your sentence, it will assign a Shapley value telling if it is supporting that classification or not supporting the classification. Now, so for what you can do is for entire corpus, you can get a big array of Shapley values, and you can do a global as well as local explanation. A global will tell you that what are some of the words. So in this case, I was looking at a particular text like joy, and it will say these are the words because of which contribute positively or negatively towards joy. So words like content or delighted contribute positively towards joy, while words like humiliated, dissatisfied, pathetic, they contribute negatively towards joy. So you can look at one particular classification like joy and see which words correspond more positively or negatively towards it. And same thing you can do for a local classification where you can take one entry like this sentence. I can go from feeling so hopeless to so damn hopeful, and you can say it is classified as sadness. But why is it classified as sadness? These are the words like hopeless in red, which have higher SHAP values, so they contribute more towards the sadness classification. While some of the other words like hopeful or who cares or awake, these words are more less contributing, but then because hopeless and it understood the meaning of the sentence, it classified this as sadness. So this is how SHAP can be used for local and global and local explanations. Now let's take some time. I think we have time, so we'll just explain a little bit about transformers because this is really important. You may have already done this in your course, so don't mind if this is like a bit of a repeat. But this is very important if you're not gone through this for text classification. So what transformers was one of the revolutionary architectures. It came out in 2018 by Google. It's that their paper "Attention is all you need," which is the famous, very highly cited paper. So what transformers is basically an encoder decoder architecture. So encoder takes your sentence sequence, encodes it into an array, and the decoder takes it out and creates a new array out of it. So for example, you can do a language translation, feeding one sequence and getting a different sequence out. Now, taking this concept, two types of models were evolved. If you look at just the encoder piece of transformer, you can have an auto encoder kind of model, and that's what BERT does. There's a this the image on the right is taken from the illustrated BERT article by Jay Lamar. This is in my references. I highly recommend it. It explains to you how BERT works inside out. But then at a high level, what BERT does is the first step is a semi-supervised training. So it takes this corpus of unlabeled text and learns from it, performs the language pre-training. So pre-training will basically it follows two approaches. One is a masked language model. So it will randomly mask 15% of words in a sentence and try to predict it. So if it can predict it, it will tune itself so these predictions get accurate. So it tries to adjust to the corpus. So you can see if it is a medical corpus and there are some words like treatment of a disease. Now these things, if it masks and tries to understand, it will start to understand the patterns of how medical languages or how banking languages. So the first step of the BERT transformer is using semi-supervised training using masked language model, and it also had one more thing for next sentence prediction, and using that to actually try to build a pre-trained model. And then the second task is you try to fine tune your model for a particular task. So if you are doing classification, saying classifying this as a medical document or a political document, you can do that. You can just apply like your softmax layer, take the uh, take the encoding. So what your encoder will do is basically create an encoding. Now that encoding you can take and apply like a softmax layer or multiple fully connected layers and do a classification. So now what happens is, because you have done this pre-training, your encoding becomes much better than your word to vec. Now word to vec will be more of it won't have your contextual information. So for example, if you take a word like river bank, word to vec will have the same encoding for a river bank as well as a financial bank, because it doesn't capture the context. But if you do this language model pre-training, like this step in BERT, it will capture the context from your text. So it will use a different encoding for your river bank and for your financial bank. So that's the advantage of using language models like BERT. it will give you a contextual encoding. And then using that contextual encoding, once you have captured the context, then you apply your supervised learning layers to do either classifications or downstream tasks like named entity recognition, etc. So that's the advantage of BERT. And while we are talking about BERT, one thing to recognize is BERT uses only the encoder part, because it is using it is creating an encoding, a contextual, context-aware encoding, and uses that encoding to make predictions. While the second part, the decoder part of transformers, is used by auto-regressive models like GPT-2 and GPT-3. What we do is they generate new text. So you say, I am taking this session on PKC because, and then it will try to fill in some sentence based on the context it has learned, like I like to share knowledge, or I'm working persistent, or something like that. So it will try to create your next sentence using in an auto-regressive way. So these are two types of models following transformers: an auto encoder model like BERT, which uses and an auto-regressive model like GPT-3. Both use language model pre-training, like unsupervised pre-training, so they can learn all the nuances of your language or that particular domain, like healthcare or banking. And then they can be fine-tuned for a particular task. Like in case of GPT, it's just generating the next sentence given a seed. But in case of BERT, it will be more a fine-tuned activity like classification or named entity recognition. So that's kind of a very high level. And sorry if you had already known about this or had already done this in your class, but that's kind of a very high level overview of transformers and how different types of transformers model work and how BERT functions. So with that, and this is a nice, this is from the transformer, illustrated transformer article, which is in the references by J. Lamar. So the idea again is what BERT does is it takes your sentence and adds certain, it does a tokenization. Now this tokenization is not at a word level, but it applies its own tokenization. It says, starts with a CLS for classification, puts a separator for SCP, and then for those tokens, it encodes those tokens into integers. And then Distilly is a version of BERT which is much more efficient, much more faster. It's more popular to be used rather than traditional BERT. So it passes through Distilly, and BERT uses self-attention mechanism, so it can take the entire sentence together rather than taking it as a sequence. So it looks at all parts of the sentence together, and then it generates an encoding like we saw earlier, and that encoding can be fed into just a regular logistic regression layer to do a classification where it is positive or negative. So that's kind of how your Distilly or BERT works. So that was a very high level introduction to what how NLP models work, how BERT works. Now we'll get into actually explaining this model. So we'll look at some abstracting examples also. So let me take a 5-minute break, and actually let's do like at 11:10. At 11:10, I'll take 10 minutes and walk through this Google Colab example. So if you know, you may have to shut down your earlier session and restart a new session, because sometimes because it is using GPUs, it may take up more of the resources. So let's start in another 4 minutes with this example. I'll just walk you through the example on explaining text model. So see you in 4 minutes. Hi everyone. So let's start with the notebook and explaining text. And again, this notebook also has all the references, especially this illustrated transformer and visual guide to BERT. I really recommend going through these two articles, because they really do a good job explaining some of the papers on BERT. Again, Shapley global explanation. This is the image that I showed earlier about using BERT 2x, the transformer architecture. And then this is about self-attention. Again, if you look at JLMR's article, you will get to know more details of this, how the self-attention mechanism works, and what BERT does under the hood. So I just read this. I just ran this cell before. Basically, because I'm running Collab, shape transformers and data sets is not something that comes by default. So I just ran it beforehand. So now what I'm doing is I'm loading one data set called emotion data set, and all this is doing is it is it will have certain text, which is so if you look at this is how the data set looks like. So it has a sentence, I didn't feel humiliated, and gives an emotion. So it gives an emotion from zero to I believe zero is sadness, to joy and a bunch of other things. Joy, we will see the list also. So now what I'm doing is I'm loading a pre-trained board. So one of the things that there is this company Hugging Face. So they are really championing the work on transformers. It started with Google, but Hugging Face really has done a great job in making it available to everybody. So they have this Python library called Transformers that you can install. And once you install, you can get access to a lot of these pre-trained models. So as we saw earlier, these models are trained on unlabeled text. So so Hugging Face has trained these models on Wikipedia and really billions of sentences, billions of words, and use these pre-trained models for certain downstream tasks. And you can just load these pre-trained models and use them for your prediction tasks. So that's what we are going to do. Just like it's very equivalent to what we did in ImageNet. We loaded a pre-trained VGG16. So same thing we are doing. We are loading a pre-trained text classification model, or sorry, a transformer model from Hugging Face. So, and now keep in mind, one thing is what we saw in the slide. We need to have a tokenizer also, because every transformer model, they may use a different tokenizer strategy. So the one that I'm using right now is, and if you go to Hugging Face, you can see like hundreds of transformer models for different cases. Like for example, there is a model which is trained on financial documents. So it is trained on in an unsupervised manner on financial documents, and it can do financial summarization well. Again, so purely transformer models, you use the same abstraction by Hugging Face to use the model, just the same code that you are seeing here, but then you can use it for a different purpose. So what I'm doing is I'm creating a tokenizer, loading the model. Because I'm on Google Colab, I'm using a GPU allowed to give this .CUDA invocation, and I'm just defining some functions which will basically take your label and convert it, take the label into an ID. So so the next thing I'm doing is taking my emotion map, the data set that I loaded, emotion data set, and finding out which all classifications are there, and putting them on a bar chart. So in a while, in a minute, the chart will come up telling you which uh, which are the classifications. So maximum are for joy. There are few data points for there are some data points for sadness, anger, fear, love, and surprise. So these are the categories in which these sentences have been classified. So this becomes our labels or ground truth, and we uh, we are going to use this to see what sort of predictions our transformer model can make. In this example, we'll use shape. So what we are doing is we are building this function which will take which will take the tensor and convert it, create shape values, shapely explanations for this, and then you run an explainer which will take a shape explainer, and for those labels it will. So shape has support for transformers architecture. So what it will do is you take, but you have to provide the tokenizer and the model. So using this function, you're converting your text into something that the transformer architecture understands, and then passing that to a shape explainer and getting the shape values. Once we do this, this may take some time. You pass the so what I'm doing is I'm passing the first 50 data points and the text, and this is because of time. Ideally, you would pass the whole corpus, and it will take a few minutes or even up to an hour uh, to build shape values for this transformers model. Now, once you have that, now what I want to do is for the class sadness, I'm creating a shape plot, a bar plot, taking the shape values and just giving sadness as the classification and finding the mean across all my data points. So now shape will give you the local explanations, but I'm trying to make them global. So once I do that, this chart is generated, which will tell me that for sadness, these are the factors that affected positively. So because the words like humiliated, pathetic, and defeated were there, that contributed to sadness in those sentences. While irritated and actually this is kind of an error, I believe. Content, romantic, these contributed to again sadness. I guess irritated is because it is compliant with some other, maybe it is with fear or surprise or something like that. Mm. So this is how it contributes to those particular values. So, so then let's get to the local explanation. So I'll take the values from 10 to 15 for so these are the five sentences from my data set and the corresponding emotions. Now what I'll do is I'll generate a Shapley plot where for those 15, I have, for those 15, I'm trying to explain. And Shep uses this concept of saliency maps. So it will give me an input-output heat map. So this is the input. I feel like I have this suffering, and these are the six classes in which it is. So if you can go on one particular say, why is it classified as sadness? So if you look at the first example, I feel like I have to make the suffering. It classifies it as a sadness. Now, why does it classify it as a sadness? So even if you can hover your mouse over it, it can tell you which are the highest shape value features. So suffering is the highest shape value feature. I feel like also sometimes this combination of words is also giving it a high value, and then have to make the is kind of becoming joy. So if you look at joy, so something like suffering is negative. Blue means it is going against, as you saw earlier, going contributing negatively to that particular classification. So and then we can do the same thing for love, anger, etc. So here we are seeing interactively. You can quickly see that for this particular classification, and this is a pretty straightforward example, but you can see for a more complex example, like if you're doing disease classification, you can say that like when a doctor is seeing, say, electronic health record, and they say this patient has this disease, he can, if you can give explanations, he or she can specify, okay, these are the words that contributed to that explanation. So because of these sentences or these words, this is why that person was detected as certain disease. So that's how you can kind of explain your text classifications. The other image you can see, I mean, you can do a heat map plot or you can do a saliency plot. So saliency plot also does the same thing. What it does is it will try to tell you that for this particular classification, like sadness, these are the combination of words. Now, this is where you have to see it doesn't look at individual words. It looks at a combination of words, which is what makes transformers unique. If you look at some of the older models, like even these latent deviation allocation, or even some of these word-to-vec models, they all focus on a single word. But transformers kind of can look at because it looks at tokenization strategy, it can look at a sentence together and try to see because of these sentences, it can classify it as joy or sadness. So that's pretty unique, and that's what has led to the success of transformers because of the tokenization strategy, the language model pre-training, and the downstream multitask classification. So it's a really advanced technology and achieving the state of the art. So going forward, we'll see a lot better models. I mean, GPT-3 was released last year, and it is able to now write text and write poetry. It can do some amazing things from artificial intelligence perspective. So transformers is definitely the future for NLP, and these models like SHAP can help you explain transformers. Before we take the questions, one last demo. I didn't really pass this notebook around, but I just wanted to show you, because most of these demos that we showed here, these are all of we have not looked at the GPT-3 kind of models, which are auto-regressive. So here, the same exact strategy. I'm not going to run this notebook, but if you see, I'm using a different transformer model here. I'm using a distillibart XSum. If you saw, this is not distillibart, but I'm using a BART model. BART is a Facebook's language model that combines your encoder and decoder, and it's for abstractive summarization. So it can generate new text for you. As you look at the decoder part of transformer, you start getting into the generative model. As you look at the encoder part, you are more getting into contextual embeddings and using that for classification, things like that. So now when we look at the decoder part of it, now we want to we use this distillibart, and then again, and what we are trying to do here is loading this data set called extreme summarization. Extreme summarization data set basically takes your a paragraph or two of text and just summarizes in one or two sentences. and it is trained. I'm training this on this extend summarization. Sorry, I'm loading the extend summarization data set. And this is an example that this is a huge, this is basically your sentence, and it is summarized, I believe, in the last sentence just as a single line. So I'm loading, we saw that example earlier. I mean, we talked about this quantum computing example. So I'm loading this paragraph on quantum computing, which I picked up from Wikipedia. And then I'm running it from a SHAP explainer here. So so the SHAP explainer is taking my transformer BART model and taking my tokenizer and generating explanations for my summary. So now these are abstractive explanations because, or these are abstractive summarization. So I'm taking my bigger chunk of text and generating 1 or 2 lines of sentences summarizing this. So so when I run this is the heat map that I get. So this is the input text that I have provided, which is a big paragraph. And this is the summary that the BART model had generated on its own. It's abstractive because you see none of this sentence is as it is into this text. They generated this from fresh. So it is abstractive in nature. And then when we do summarization, you can say, so why has it used Waterloo as a word? As one of the tokens. Why is it used Waterloo? This is because this sentence, according to the Institute of Quantum Computing at the University of Waterloo, this sentence had Waterloo. So instead of taking the whole sentence, it was smart enough, this transformer model, to say that, okay, use Waterloo and generate an abstractive sentence. So you can see that, I mean, if you look at summarization, how, this is more resembling how a person would do. A person would read that sentence according to the Institute of Quantum Computing at University of Waterloo, field of computing starting in 1980s. Uh, it doesn't even take the 1980s, but it says that quantum computing was developed by University of Waterloo. So this is how a human would do it. Now, it may not be the perfect summarization, but what you should appreciate is it is abstractive in nature. It is writing the summary on its own. So more you train it with better sentences and better summaries, it will try to write much better summaries. Similarly, why did it use University of Waterloo is the same sentence. Why did it use supercomputer is because it used some of these sentences. So this kind of tells you why that's, and the same thing, you can do a saliency plot where now you can see that the summary that is being generated, a new class of supercomputer called quantum computer is being developed by University of Waterloo in Canada. For each of these tokens which was generated by it, what was the evidence behind it? So it generated this super because this sentence from the input had that supercomputers in it. So you can see that, so this gets into, so we saw here transformers, the abstractive summarization using transformers. And now we are getting into explaining these transformers using saliency maps and heat maps, using figuring out which sentences are important for which generated text. So I just wanted to run this example because I didn't know if we would have time, but luckily we had time, so we could go through. So that's kind of that's all about text models and summarization and generative the autoencoder models and auto regressive models. So let me. So that was all I had to cover. And coming to the slides again, I have given references for a lot of material and the figures that I've used. References are there here as well as in the notebooks that I distributed. And again, I'm on LinkedIn and I've provided my email, so we can, if we don't get time now, we can also discuss or answer any questions offline. Let me see if there are some questions which I can quickly take. Uh, there is one on yeah, the one that Dr. Sham's 7 5 some specifics on the 7 by 7 to full image. I think yeah, I think, okay. So yeah, if you look at the notebook, Dr. Sham, I think that will have some of these explanations how the mapping is done. But we can connect offline also on that. And then yeah, then the Trupti says uh, some details on wave to whack. Yeah, so wave to whack is also interesting. I personally am not tried much of it. I just used it in one notebook, but the idea is the same. And if you look at any media to, if you want a machine learning to analyze it, you want to convert it to a vector, an image into a array, three-dimensional array, or a word into a vector, or like wave. So I think wave to whack, if I understand it right, it takes your a wave file an audio file and converts it into a sequence of vectors. And depending on the frequency, different frequencies, and that sequence then can be fed to an LSTM or an RNN layer to extract some content on it. So you can classify your audio and things like that. A lot of time, I think it is used for transcoding, where you can take your wave file and convert it into a sentence. So you do a similar sequence to sequence. And I believe transformers have been, and I may be wrong here, transformers have been used for that also, where you take a wave to vec model and use transformers to extract this thing. Again, I'm not an expert on this, but the concept is the same, I would say. Yeah. So Prasanna says summarization attributed quantum computing, how to correct such mistake. Yeah, that's a good point. So the summarizations are not definitely, the summarization is not foolproof. It's an active area of research, and a lot of this. Yeah, so a lot of times the summarizations, abstractive summarizations do have mistakes. In fact, things models like GPT-3, even the question answering, you're not sure. I mean, I wrote an article on that same thing also. They tend to assume certain things, and they tend to make mistakes. So how to correct it? I guess explanations is a start. If along with your, when you actually use these models in production, if you know the explanations, at least you should know what sentences are used for why would you for that particular what sentences are used to make that particular abstractive sentence. So if you can at least explain those, then you can have a human make a decision that the right sentences were used. Because many times if you have a big paragraph, the self-attention works at a sentence level, but you may miss some things, and sometimes the text itself may be contradictory. In one sentence you may say a fact, and the second sentence it may be counterfactual. So it is very difficult for a model like this. So and that is all makes all the more important to have explanations. So if you have explanations, you can actually try to explain this and at least correct some of these mistakes. But you're right. I mean, this is not a foolproof. By no means is it a foolproof method, and explanations definitely are needed. Especially, I mean, these things are smaller mistakes. But if you get into a bias, if they are making politically incorrect sentences, you don't want a model to abstractly make politically incorrect sentences. So, yeah. Oh, thanks, Dr. Sham and Prasanna. So I think that those were the questions, and we are right on time. So I hope this was helpful, and thanks for the wonderful comments, Dr. Sham and Trupti. So do connect with me offline or over LinkedIn.
There was a lot of insights from the session, and I hope it is useful for for people who attended this session. So thank you so much. We'll meet next Monday for the next session of the course, and you can get connected with Mr. Dattaraj on email and so on. So yeah, thank you so much.
Yeah, thank you, everyone.